For most of human history, the outer edge of the solar system sat at a clean, comfortable distance, and astronomers had the numbers to prove it. Neptune, the farthest known planet, orbits roughly 30 times farther from the Sun than Earth does. Beyond that, the thinking went, there was essentially nothing. A vast stretch of cold, empty space before the distant Oort cloud swallowed everything. The solar system had a boundary, and we knew where it was. That picture was wrong. Not slightly wrong. Wrong in a way that should genuinely embarrass the textbooks that taught it. Beyond Neptune, starting roughly where that planet's orbit traces its path and stretching outward for billions of miles, there is an entire province of the solar system that almost nobody talks about. It is called the Kuiper Belt. It is enormous. It is ancient. It is filled with hundreds of thousands of icy bodies, frozen remnants from the formation of the solar system, sitting out there in the dark at temperatures close to absolute zero. Most people have never heard of it. Most people have certainly never thought about it. And right now, it is the most interesting place in planetary science. Here is what astronomers have found. There are objects sitting at distances of 70, 80, even 90 times the Earth's distance from the Sun, in a region where current models say almost nothing should be. There is a sharp, abrupt cliff in the population of Kuiper Belt objects at roughly 50 astronomical units. A cliff that drops off with a precision that random physical processes cannot cleanly explain. There is a gap in the outer solar system, a structured empty zone that looks disturbingly familiar to astronomers who study debris disks around other stars. In other planetary systems, gaps like this have one standard explanation. A planet made it. And there is a small frozen body, about 500 kilometers across, sitting in the deep cold of the outer solar system that appears to have an atmosphere. That last one should not be possible. Were we wrong about where the solar system ends? The answer is almost certainly yes. Were we wrong about how active and complex the outer solar system is? Also yes. And the question sitting underneath all of it, the one that has driven a decade of serious scientific debate, is whether something large and unseen is out there, pulling strings, sculpting the architecture of the outer solar system from a distance so extreme that centuries of sky surveys missed it entirely. A hidden planet, not Pluto, something far larger, far more distant, and far more consequential. The evidence for it has been building for years. The machine that might finally confirm it just came online. What the Kuiper Belt is actually hiding may turn out to be the most important discovery in the history of planetary science, and we are almost certainly looking right at it. Beyond the orbit of Neptune, roughly 30 times farther from the Sun than the Earth is, the solar system does something unexpected. Instead of fading into empty space, it fills back up. Not with planets, not with anything large enough to see with the naked eye, but with billions and billions of frozen objects drifting in slow, cold orbits around a sun so distant it barely qualifies as a star. This region has a name: the Kuiper Belt. Most people have never had a reason to think carefully about it, and that is part of the problem, because once you understand what it actually is, it becomes very hard to think about the solar system the same way again. Start with the basics. An astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. That is the unit astronomers use when the numbers get too large for anything more familiar. Earth sits at 1 astronomical unit, Mars at about 1.5, Jupiter at 5.2, Saturn at just under 10, Uranus at 19, and Neptune, the outermost recognized planet, sits at about 30 astronomical units. That is 30 times the Earth-Sun distance, which works out to roughly 2.8 billion miles. A passenger jet flying continuously at cruising speed would take somewhere around 600 years to reach it. The number is almost impossible to hold in your mind. Neptune is not close to anything. Now take that distance and double it. The Kuiper Belt starts right around where Neptune orbits and extends outward to roughly 50 or 55 astronomical units. That range, from 30 to 55 astronomical units, is the classical Kuiper Belt. The inner solar system, everything from the Sun out to Neptune, fits inside a sphere of 30 astronomical units radius. The Kuiper Belt adds another 20 to 25 astronomical units on top of that. Because volume scales with the cube of distance, the sheer space enclosed by the Kuiper Belt dwarfs the region containing every planet most people have ever heard of. It is an enormous territory, and it is not empty. The belt was theorized long before any objects were actually observed. In the 1940s, astronomers Gerard Kuiper and Frederick Whipple independently proposed that a region of icy bodies must exist beyond Neptune. They reasoned from orbital mechanics and the presence of certain comets that no model of the solar system made sense without it. But for decades, the belt remained theoretical. Actual discovery of its objects began slowly in the 1990s, accelerated through the 2000s, and continues today. Each new detection adds another piece to the picture. The belt, in other words, has only recently become real to us, even though it has been there since the solar system began. The objects in the Kuiper Belt are not rocky in the way asteroids are. They are icy, frozen water, frozen methane, frozen ammonia, sometimes mixed with silicate rock and carbon compounds in proportions that vary from one object to the next. The sun's heat barely reaches them, and so these materials remain locked in ice rather than boiling off into space. At 40 or 50 astronomical units, the temperature hovers somewhere around -220 degrees Celsius. The objects don't change much. They have been sitting out there, slowly orbiting, since the solar system was young. They are in some ways the best preserved material from the original disk of gas and dust that everything else formed from, nearly 4.6 billion years ago. What they look like, surprisingly, is not uniform. Kuiper Belt objects span a remarkable range of colors. Some are dead white, reflecting sunlight the way fresh snow does. Others are neutral gray, and some, particularly the ones found at greater distances or in specific orbital populations, are extraordinarily red. Not a subtle tint, but a deep, rusty, almost blood red that astronomers describe as ultra-red. This color comes from complex organic compounds called tholins, which form when ultraviolet radiation from the sun slowly processes methane and nitrogen ices over hundreds of millions of years. The color itself is a clock. The reddest objects have been cooking in sunlight for the longest time, sitting undisturbed in the outer belt, accumulating chemistry that has nowhere else to go. There are a lot of them. Estimates suggest hundreds of thousands of Kuiper Belt objects with diameters larger than 100 kilometers. That is roughly the width of the state of Kentucky. Objects at that scale, in the asteroid belt, would be notable individually. In the Kuiper Belt, there are hundreds of thousands of them. Extend the count down to smaller sizes, and the number climbs into the trillions. The Kuiper Belt is not a sparse scattering of lonely ice balls. It is a vast, crowded, structured population of frozen material, spread across an enormous volume of space, largely invisible from Earth. And then there is Pluto. Pluto is the most famous resident of the Kuiper Belt, though nobody knew it was a Kuiper Belt object when it was discovered in 1930. For 76 years, it was classified as the 9th planet. Then, in 2006, the International Astronomical Union downgraded it to dwarf planet status, and the cultural backlash was significant. People felt that something had been taken away. Here is what actually happened. By the early 2000s, astronomers had been finding other objects in the outer solar system that rivaled Pluto in size. Eris, discovered in 2005, was actually slightly more massive. Makemake, Haumea, others. The Kuiper Belt was revealing itself as a population of similarly sized bodies, and Pluto was not a lonely outlier beyond Neptune. It was one of many. The definition of planet had never been designed to handle this situation, and when the IAU finally revised it, Pluto fell below the threshold. What the demotion really meant was something stranger and more interesting than any reclassification. It meant the outer solar system was crowded in a way nobody had fully appreciated. It meant Pluto was a representative of a type, not a singular oddity. And it meant that for most of the 20th century, astronomers had been looking at the Kuiper Belt's most famous member without recognizing it as part of a much larger structure. The Pluto story is not a story about scientific bureaucracy making a mistake or correcting one. It is a story about a part of the solar system becoming visible for the first time, slowly, one object at a time, until the picture finally forced a reckoning with how large and complex the outer solar system had always been. Pluto's demotion did not shrink the solar system. It revealed just how much of it had been invisible all along. In 1992, after 5 years of searching through images of the outer solar system by hand, David Jewett found something that was not supposed to be there. The story starts earlier than that, though. In the late 1980s, Jewett was a young astronomer at MIT with a specific and unfashionable conviction. He believed that beyond Neptune, beyond Pluto, beyond the lonely edge of what most textbooks called the solar system, there had to be more. The theoretical argument was not his alone. Gerard Kuiper had gestured toward it in the 1950s. Fred Whipple had similar instincts. The mathematics of how comets behaved hinted at a reservoir of icy bodies somewhere out beyond the known planets, a source population that could explain where short-period comets were coming from. But mathematics and instinct are not the same as evidence. Nobody had ever seen a single object out there. And in astronomy, until you can show someone a picture, you have nothing. What Jewett had was a plan and a new piece of technology that most astronomers were only beginning to understand how to use. The instrument was a CCD camera. Charge-coupled devices had been quietly transforming optical astronomy since the late 1970s. Where photographic film captured perhaps 1% of the light falling on it, a good CCD could capture 80 or 90%. That is not a modest improvement. That is the difference between looking at the outer solar system through a window and looking through a wall. Objects that were genuinely invisible to photographic surveys could suddenly be detected. Jewett recognized this immediately. He teamed up with Jane Liu, a graduate student at MIT, who brought both technical skill and extraordinary patience to the project. Together, they set out to use CCD imaging to search a region of sky that most of the field had quietly written off. The search itself was not glamorous. It was 5 years of pointing a telescope at patches of sky, taking exposures hours apart, and then comparing the images by eye, looking for any point of light that had moved. Objects in the outer solar system move slowly. Neptune takes 165 years to complete one orbit. Anything further out moves even more sluggishly against the background of fixed stars. But slowly is not the same as invisibly, and Jewett and Liu were looking for exactly that kind of motion. They were using a 2.2-meter telescope on Mauna Kea in Hawaii, one of the best sites on Earth for this kind of work. The altitude keeps you above most of the atmosphere's blur. The dark skies keep the background noise low. Then, on the night of August 30th, 1992, a point of light moved. It was faint, roughly 100 times too dim to see with the naked eye. It was slow, as expected, and it was sitting far out in the solar system, well beyond Pluto, in a place where nothing should have been orbiting the Sun at all. The object was designated 1992 QB1. It would later be given the name Albion. On that single night, the known solar system got larger in a way it had not since the discovery of Neptune in 1846. Here is the thing worth sitting with for a moment. The object had always been there. It had been circling the Sun for billions of years while the dinosaurs rose and fell, while mammals evolved, while human beings invented writing and telescopes and CCD cameras. The solar system had not changed. Our ability to see it had. That distinction is one of the stranger ideas in the history of astronomy. A province of the solar system the size of a continent had been invisible not because it was hidden in any dramatic sense, but simply because the instruments to detect it did not exist. Within a year, a second object appeared, then more. The pace picked up steadily. By the mid-1990s, dozens of trans-Neptunian objects had been found, each one confirming what the discovery of Albion had implied. This was not an anomaly. There was a belt out there, a genuine population of icy bodies spread through a wide ring beyond Neptune, orbiting in relative quiet at distances that made them extraordinarily difficult to study, but not, with the right tools, impossible to find. The shift in how astronomers thought about the outer solar system was dramatic. Before 1992, the picture looked like this: the 4 giant planets, then Pluto sitting awkwardly at the edge, then essentially nothing until the Oort cloud at distances of thousands of astronomical units. The region from roughly 30 to 50 astronomical units was simply blank on every conceptual map. A gap, not a mystery, just space. Nobody expected it to be populated because nothing had been found there, and nothing had been found there in part because nobody had looked with instruments capable of finding it. After 1992, that blank region had a name, a population, and a growing catalogue. The Kuiper Belt was real. Pluto, which had always seemed like an oddity, suddenly made sense as the largest known member of a vast family of similar objects. Pluto's strangeness resolved. It was not an outlier. It was simply the first of its kind that anyone had found, and it had been waiting nearly 60 years for company. The catalogues grew fast. A few dozen objects became a few hundred, then 1,000. Surveys improved. CCDs got more sensitive. Telescope time devoted to outer solar system searches increased as the scientific payoff became undeniable. The questions that came with each new object multiplied as quickly as the objects themselves. Where did they all come from? What was the outer boundary of this belt? What determined their orbits? And was there anything even further out, in the dark beyond the dark? By 2018, more than 2,000 Kuiper Belt objects had been catalogued, and the number was still climbing. But the strangest discoveries were only just beginning. The Kuiper Belt does not fade gradually into empty space the way most people imagine the edge of the solar system should look. Most people, if they picture the outer solar system at all, probably imagine something like a beach fading into water. Objects getting sparser, more spread out, the density dropping off slowly until there is simply nothing left. That is a reasonable thing to imagine. It is also not what happens. What actually happens at roughly 50 astronomical units from the Sun is something far stranger. The population of Kuiper Belt objects falls off a cliff, not a slope, not a gradual thinning, a cliff. The number of objects drops sharply and dramatically, and then beyond that point, there is essentially nothing where the models said there should be something. Astronomers have a name for this. They call it the Kuiper Cliff, and it has been sitting in the data, largely unexplained, for decades. To understand why the cliff is so troubling, you have to understand what the models predicted before anyone knew it was there. When researchers first worked out the structure of the outer solar system in the 1990s, they built their expectations on the physics of how planetary systems form. A young star surrounded by a spinning disk of gas and dust is a system with momentum and mass distributed across enormous distances. The disk that formed our solar system extended far beyond the orbit of Neptune. It had to, because the outer planets are where they are, and they had to have material to form from. By every reasonable estimate, that primordial disk stretched well past 50 astronomical units. Some models put its outer edge at 70, 80, even farther. The material out there would have been thinner than in the inner disk, but it should have been present. Objects should have formed from it. When Jewett and Liu confirmed the Kuiper Belt in 1992 and the catalogue of known objects began to grow, scientists started measuring how the population changed with distance. The result matched the models reasonably well, out to around 50 astronomical units. Then came the cliff. Researchers ran the numbers. They checked for observational bias. It would be easy to miss objects at extreme distances simply because they are faint and slow-moving, and surveys have limits. The first obvious question was whether the drop-off was real or whether it was just an artifact of what the telescopes could detect. Gary Bernstein, David Trilling, and their colleagues published careful analyses that addressed exactly this. When they accounted for detection limits and survey coverage, the cliff remained. The drop-off in objects larger than 100 kilometers in radius beyond 50 astronomical units was real. It was not a gap in the catalogue. It was a gap in the actual population. That is the part that bothers astronomers. Not that the objects are hard to find beyond 50 astronomical units, but that there genuinely seem to be far fewer of them than there should be. The primordial disk was there. The raw materials were there. Something happened to the objects that should have formed from those materials, or to the materials themselves, before the objects could form. And whatever happened, it drew a remarkably clean line at 50 astronomical units. The leading explanations divide roughly into three categories, and none of them is entirely satisfying. The first is that the material beyond 50 astronomical units was simply too sparse and too dynamically scattered to build large objects in the first place. In the inner Kuiper Belt, the density of material was high enough for small bodies to collide, stick together, and grow. Further out, those collision rates may have been too low. Objects that started growing would have had too few encounters to continue growing, and the process would have stalled before anything substantial could form. This explanation has a certain appeal. It requires no exotic physics, just the natural consequence of a thinning disk. The problem is that when you run the numbers carefully, the disk shouldn't have thinned that sharply, that quickly, at exactly 50 astronomical units. The cliff is too clean. The second explanation involves gravitational sculpting during the chaotic early period of the solar system. The giant planets, particularly Neptune, migrated outward during the first few 100 million years of solar system history. As Neptune swept through the outer disk, it scattered enormous amounts of material. Some of it was thrown inward, some was thrown outward into the Oort cloud, some was ejected entirely. It is entirely possible that the material which should have populated the outer Kuiper Belt was simply cleared out by this process, leaving the cliff as the scar of Neptune's migration. This is a plausible story, but matching the exact shape of the observed drop-off is difficult. The models produce a smoother decline than what the data shows. The third explanation is the one that is hardest to dismiss and hardest to prove. Something large might be out there. A massive undiscovered body sitting beyond 50 astronomical units in a distant orbit would exert gravitational influence on the surrounding population over billions of years. It would scatter nearby objects, perturb orbits, clear material from the region around it, and potentially carve a sharp edge into the Kuiper Belt's outer boundary. Patrick Likavka of Kobe University and his colleagues have argued this case specifically, that the gravitational signature of a hidden planetary mass object, perhaps the size of Earth or Mars, is the most natural explanation for why the cliff exists where it does and why it is so abrupt. An object of that kind, in an orbit far enough out to have escaped detection, would do exactly what the data seems to show something did. Here is the strange thing. When you look at the cliff from a distance, it resembles nothing so much as a boundary that was imposed rather than a boundary that simply emerged. Natural processes in a thinning disk produce gradual fall-offs. They produce curves, not edges. The sharpness of the Kuiper Cliff, the precision of it, is the feature that keeps drawing theorists back toward the idea that something active created it. This is not yet the Planet 9 story. That comes later, with its own evidence and its own debate. But the cliff is where the question first appears in the data, sitting at 50 astronomical units, like a wall someone built across the outer solar system. Something cut the Kuiper Belt off at 50 astronomical units, with a precision that random physical processes have no good explanation for, and the candidates for what did it are limited. On July 14th, 2015, after traveling more than 3 billion miles through space in 9 years of continuous flight, New Horizons swept past Pluto at 31,000 miles per hour and sent back images that nobody was fully prepared for. The expectation, going in, was something like the Moon. A battered, frozen ball, pocked with ancient craters, geologically dead for billions of years. That expectation was reasonable. Pluto sits so far from the Sun that the solar heating reaching its surface is negligible. There was no obvious reason for it to be anything other than a relic, interesting as a historical artifact, but inert. What the cameras showed instead was almost unsettling. Pluto had mountains, real ones, rising 2 miles above the surrounding plains, built from water ice so cold it behaves like rock at those temperatures. It had vast, pale nitrogen glaciers flowing across its surface in slow, creeping sheets. It had a thin but confirmed atmosphere, haze layers stacked above the surface, glowing faintly in the backlit, images that New Horizons captured as it swung past. The world that the textbooks had essentially written off turned out to be one of the more geologically complex objects in the outer solar system. The most striking feature was the one that became immediately famous: a broad, heart-shaped basin covering an area roughly the size of Texas and Oklahoma combined, now called Tombor Regio, after the astronomer who discovered Pluto in 1930. The western half of the heart, a smooth, pale expanse of nitrogen ice, showed almost no impact craters at all. No craters means a young surface, a surface being continuously reshaped. Something was happening on Pluto, geologically speaking, and scientists are still debating exactly what that heat source is. The terrain elsewhere on the surface swung between extremes: dark, heavily cratered ancient highlands on one side, bright smooth plains on another, a jumbled region of chaotic broken terrain that researchers nicknamed the Bladed Lands. Whatever Pluto was, it was not simple. The flyby lasted roughly 1 day at closest approach, but the data took more than a year to fully download. New Horizons was so far away that the radio signal, traveling at the speed of light, took 4.5 hours to make the one-way trip to Earth. Every image, every measurement, every data point arrived slowly, and each one added something unexpected. Pluto was not the dead world the models predicted. It was active, strange, geologically varied in ways that forced a serious rethinking of what small, cold bodies at extreme distances are capable of. But New Horizons did not stop at Pluto. That was always the plan. The spacecraft continued outward into the Kuiper Belt. Mission planners had already selected a second target before the Pluto flyby even happened: a small, distant object discovered by the Webb Space Telescope in 2014 and designated 2014 MU69. It was later named Arakoth, a word from the Powhatan language meaning sky. On January 1st, 2019, New Horizons made its second flyby, this time at a distance of roughly 4 billion miles from the Sun. No spacecraft had ever visited an object that remote. What Arakoth looked like was not what anyone had predicted. It was a contact binary, 2 distinct lobes pressed gently together. The larger one, roughly 22 kilometers across, and the smaller one about 14 kilometers, connected at a narrow neck. The whole thing resembled, in the images that came back, something between a snowman and a peanut. It was covered in a reddish material, a kind of organic coating called tholins, produced when simple molecules like methane and nitrogen are bombarded by radiation over billions of years. The surface was smooth, heavily cratered, as you might expect of an object sitting undisturbed for 4.6 billion years, but smooth between those craters. No evidence of violent collision, no signs of a catastrophic impact history. That smoothness was the key detail. If Arakoth had formed through the violent collision and sticking process that most models assumed for small outer solar system bodies, it should have shown damage. the collision that merged two objects into a single contact binary under the old model, would have been energetic enough to fracture, deform, or roughen the surfaces involved. Instead, Arrokoth looked like it had been assembled gently. What the data actually supported was something called the streaming instability model, a process in which a cloud of small particles in the early solar nebula gradually concentrates under its own gravity, collapses, forms a bound pair without any high-speed impact at all. The two lobes of Arrokoth had been orbiting each other slowly, drifting together over lions of years, until they finally made contact at low enough speed to stick rather than shatter. Quiet, deliberate, almost careful by the standards of solar system formation. This was not a minor refinement of existing theory. It was a significant shift. The collision-based model had dominated thinking about small body formation for decades. Arrokoth replaced it with something more subtle and, in a way, more elegant. While all of this was happening, New Horizons instruments were also registering something else during the years of cruise through the Kuiper Belt. The spacecraft's dust counter and various detectors were picking up faint signals from small particles and objects in the surrounding environment. The counts did not fall off the way they were supposed to at the classical Kuiper Belt boundary, around 50 astronomical units. There was material out further than the maps accounted for, sparse but real. It was the first in situ measurement hinting that the Kuiper Belt's outer edge might not be where decades of observation had placed it. The cliff that surveys had identified was a feature in the large object population. Beneath it, in the background, something continued. That quiet instrumental signal would eventually be confirmed from the ground, would force a fundamental revision in how large the solar system's outer disk actually is. Arrokoth's gentle two-lobed shape was not the result of a collision. It was the result of two objects slowly finding each other across empty space. That single fact rewrote the leading theories of how the outer solar system was built. In 2023, a team analyzing data from Japan's Subaru telescope quietly announced something that the planetary science community had not anticipated. They had found objects, not one or two, not a handful of borderline detections that could be explained away as noise. A statistically significant population of Kuiper Belt bodies sitting at distances between 70 and 90 times the Earth's distance from the Sun. That is nearly double the classical Kuiper Belt boundary. The maps said this region was empty. The maps were wrong. To understand why this matters, you have to hold two numbers in your mind. The classical Kuiper Belt extends from roughly 30 to 55 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. Neptune sits at about 30. The belt runs outward from there, thinning and dropping off sharply near 50 to 55 astronomical units. Beyond that edge, the models said there was essentially nothing until the Oort cloud, a vast shell of comets so distant it barely counts as part of the same solar system. The Subaru observations found objects at 70, 80, even close to 90 astronomical units. That is not a slight extension of a known boundary. That is discovering a room in a house you thought you had fully mapped. The team behind this work was led by researchers connected to the New Horizons mission. The same spacecraft that flew past Pluto and then Arrokoth had also accumulated compelling evidence during its journey that something was out there beyond the classical belt. The Subaru telescope gave them the power to follow that thread. The Hyper-Suprime Cam instrument mounted on Subaru is built for exactly this kind of search. Wide field, deep sensitivity, the ability to detect faint, slow-moving objects against a crowded background of stars. Without an instrument at that level, the objects at 70 to 90 astronomical units would have remained invisible. They are not just distant, they are extraordinarily dim. Here is something worth sitting with for a moment. A Kuiper Belt object at 50 astronomical units receives roughly 1/2500th of the sunlight that Earth receives. Push that object out to 80 astronomical units, and the sunlight hitting its surface drops by another factor of more than 2.5. What little light reaches it reflects back toward us across a vast distance, arriving at Earth as a signal so faint that distinguishing it from background noise requires patience and precision. These objects also move slowly across the sky. At those distances, even a body traveling at tens of thousands of miles per hour appears nearly stationary over weeks of observation. Finding them means stacking images, looking for tiny shifts in position, and ruling out artifacts. It is painstaking work. The fact that this population had gone undetected before is not really a failure of astronomy. It is a consequence of physics and instrument limits. The right tools simply did not exist until recently. What the Subaru data showed was not random scatter. The 11 objects detected beyond the classical belt were distributed in a way consistent with a real population, not a collection of outliers flung there by unusual gravitational kicks. Team member Dr. Fumi Yoshida put it plainly. Either the Kuiper Belt extends farther than anyone thought, or there is a second Kuiper Belt sitting beyond the one mapped in the 1990s. Both possibilities are significant. Both imply a solar system that is larger, more structured, and more populated than the standard model predicts. Researcher Wes Fraser made a point that cuts to the heart of this discovery. Our solar system had long appeared unusually small and compact compared to the debris disks observed around other stars. Astronomers studying young planetary systems in infrared light routinely see wide, extended rings of material reaching out to enormous distances from their parent stars. Our solar system, by comparison, looked truncated, modest, a little underwhelming relative to the cosmic norm. Fraser's argument was direct. That impression was built on an observational bias. Previous surveys had simply not searched deeply enough at the right distances. The instruments were not sensitive enough. The survey areas were not wide enough. We had been measuring the solar system with a ruler that stopped too soon and concluding the solar system was short. If the Subaru detections hold up, and subsequent observations are expected to test this, the primordial solar nebula from which our solar system formed must have extended much further than current formation models allow. The raw material for planets and minor bodies was out there at 70, 80, and 90 astronomical units when the solar system was young. Something shaped that material into the population we are now beginning to detect. Understanding what did the shaping and why the region between 55 and 70 astronomical units appears relatively empty while material reappears beyond it is the next layer of the problem. That gap is not random. Gaps in debris disks rarely are. There is something almost unsettling about this discovery. The Kuiper Belt was confirmed in 1992. It has been studied intensively for more than 30 years. Thousands of objects have been catalogued. Major spacecraft have been sent through it. And yet a substantial population of bodies, not single oddities, but a real statistical grouping, went undetected until a deep field survey looked carefully enough. The outer solar system has been keeping this to itself across the entire history of modern planetary science. The comparison to other planetary systems is the part that shifts perspective most sharply. When astronomers image debris disks around distant stars, they are seeing the equivalent of our Kuiper Belt from light years away. Those disks are large, extended, often showing multiple rings separated by gaps. For years, the working assumption was that our system was different, quieter, more contained. That assumption shaped theories of how our solar system formed and influenced how astronomers compared us to the rest of the galaxy. The extended belt data suggests we were comparing ourselves to other systems while missing a significant part of our own. Our solar system, which had seemed modest and compact compared to the sprawling debris disks observed around distant stars, may have been hiding its own outer reaches in plain sight. Between roughly 55 and 70 times the Earth's distance from the Sun, the outer solar system goes quiet, not gradually, not the way a city fades into countryside as you drive away from it. The transition is sharper than that. Objects exist on one side of this zone, and then there is very little on the other side of it. And then, as we discussed, objects start appearing again at much greater distances. The gap sits between the outer edge of the classical Kuiper Belt and the newly detected distant population, and it has edges that are defined enough to be troubling. Random physical processes don't produce that kind of structure. Empty regions with clean boundaries are a signature of something that carved them out. The width alone is striking. 15 astronomical units of space. That's roughly the distance from the Sun to Uranus, compressed into a gap between two populations of objects in the outer solar system. If you drove that stretch at highway speed, without stopping, the trip would take you more than 150 million years. It is not a subtle dip in object density. It is a hole in the distribution, and it is sitting right where, based on the formation models, material had every reason to exist. This is what makes the gap different from the Kuiper Cliff. The cliff drops off at 50 astronomical units and could, in principle, be explained by the way material was distributed in the early solar nebula or scattered by Neptune's migration. The gap is a separate feature entirely. It sits beyond the cliff, between two populations that both appear to be real, and it behaves like a cleared lane. That distinction matters because cleared lanes have a well-understood cause. Here is where the comparison to other planetary systems becomes impossible to ignore. Over the past 2 decades, telescopes like the Atacama Large Millimeter Array, ALMA, have produced images of planet-forming disks around young stars that look almost nothing like what we imagined the early solar system looked like. They are not smooth, featureless disks of material. They are structured. They have rings. They have gaps. In image after image, these disks show dark bands cutting through the bright material, often at multiple radii, often with relatively clean edges. When astronomers first saw this pattern, the debate over what caused it lasted only a few years. The current consensus is that those gaps are carved by planets. A planet orbiting inside a disk of material gravitationally sculpts as the material around it. Debris in its orbital path gets swept up. Debris near its orbit gets ejected or pulled into orbital resonances that move it elsewhere. What's left behind is an empty ring, centered on the planet's orbital path, with populations of smaller objects on either side. The physics here is not exotic. We have watched Neptune do a version of this to the Kuiper Belt itself over the history of the solar system. Neptune's gravity has cleared certain orbital zones and populated others with resonant objects. Pluto is in one of those resonances. The process is known, repeatable, and leaves a recognizable fingerprint. What the disks around other stars show, over and over, is that fingerprint at larger scales. The gap between 55 and 70 astronomical units in our own system has that same shape. An underdense region sitting between two denser populations, with edges that are more abrupt than gradual dispersal would produce. If an undiscovered body were orbiting somewhere in that range, on a roughly circular or moderately elongated path, its gravitational influence over billions of years would produce something that looks very much like what we observe. It would clear objects from its immediate vicinity, creating the empty zone. It would leave the populations on either side largely intact. The structure would be stable over long timescales, because once a planet has cleared its lane, the objects that remain are the ones that have survived, either far enough away to be mostly undisturbed or locked into resonances that keep them safe. Now, the critical thing to hold on to here is that the gap does not prove there is a planet. Astronomers are careful about this distinction, sometimes to the frustration of everyone outside the field. What the gap proves is that there is a structured absence of material in a region where, based purely on the distribution of objects on either side, you might have expected material to exist. There are other explanations. The primordial disk may have had a density feature there from the beginning. Dynamical processes during Neptune's outward migration may have preferentially cleared that region without leaving a body behind. These alternatives are not implausible, but they are also not as clean as the planet explanation, and they require the gap to be a coincidence, an artifact of formation or scattering that happened to produce something that looks, almost precisely, like what a planet would produce. That is the uncomfortable position the gap puts theorists in. To dismiss it, you have to argue that a structure which, in every other planetary system we have studied, would be interpreted as a gravitational signature, is something different here. You have to argue that the solar system, which we know had an extremely violent early history involving migrating giant planets and massive scattering events, somehow produced this specific, bounded, relatively clean empty zone through a process that didn't involve anything sitting there now. That argument is possible. It is not obviously winning. What the gap does, more than anything else, is force the question into the open, because the alternative to having a planet there is not having no explanation. It is having a less satisfying explanation. And in planetary science, the record of what happens when something looks like a planet has shaped the orbit of smaller bodies nearby, the record is fairly consistent. You look harder, you look more carefully, you point better instruments at the problem, and either you find something or you don't, and both outcomes tell you something real about how the solar system works. In any other planetary system, a gap shaped like this would have astronomers reaching for the planet hypothesis almost immediately. And in our own system, that is exactly what some of them have been doing. In January of 2016, two astronomers at the California Institute of Technology published a paper that caused an immediate stir in the planetary science community. Konstantin Batygin and Mike Brown had not found a new planet. They were careful to say that. What they had found was something stranger in some ways. a pattern hidden inside data that already existed, a signal that nobody had thought to look for in quite the right way. And once you saw it, it was almost impossible to explain away. The starting point was a small set of objects, 6 Kuiper Belt objects, all of them at extreme distances from the Sun, all of them in orbits that took them far out into the cold outer solar system before looping back in. These were not ordinary Kuiper Belt objects, sitting between 30 and 55 astronomical units. These were distant scattered bodies reaching hundreds of astronomical units at their farthest points. Individually, none of them looked particularly special. But Batygin and Brown noticed something when they looked at them together. The orbits were lined up, not roughly, not approximately. Their closest approach points to the Sun, the technical term is perihelion, were all pointing in the same general direction through space. Their orbital planes were all tilted the same way relative to the rest of the solar system. 6 objects, 6 independent orbits, all sharing a striking geometric alignment that had no obvious reason to exist. The probability calculation was what stopped people cold. If the orbits were distributed randomly, the chance of seeing this kind of clustering by accident was roughly 1 in 15,000. That is not impossible, but it is the kind of number that makes careful scientists sit up straight. Random processes in the outer solar system do not produce clean, repeating alignments. The scattered disk is chaotic. Objects get flung to extreme distances through gravitational encounters. Their final orbits depend on the specific details of each encounter. For 6 objects to independently settle into orbits pointing the same direction, with the same tilt, without some organizing force holding them there, is deeply unlikely. Here is the thing that made the hypothesis click. An orbiting planet can do exactly this. If a massive body is moving through the outer solar system on its own elongated orbit, its gravity reaches out over millions of years and slowly nudges nearby objects. Not through direct close encounters, the distances are too vast for that, but through a slow, accumulated gravitational influence called secular resonance. The planet doesn't have to pass close to each object, it just has to exist, pulling steadily in a direction that gradually herds the orientations of smaller orbits into alignment. This is not a new concept in planetary science. Neptune has been doing the same thing to Pluto and a whole family of objects called Plutinos for billions of years, locking them into stable resonances that keep them out of Neptune's path. What Batygin and Brown were proposing was the same mechanism, operating at a far greater scale. Gravitational sculpting of this kind leaves unmistakable marks on the architecture of orbital systems. The fingerprints persist even across vast timescales, evidence that some unseen architect has been at work shaping the orbits of distant bodies. Their prediction was specific, and specificity is what gives a scientific hypothesis teeth. Planet 9, as they named it, should have a mass somewhere between 5 and 10 times that of Earth. Its orbit should be enormously elongated, carrying it to perhaps 200 astronomical units at its nearest approach to the Sun, and far beyond 1,000 astronomical units at its farthest. The orbital plane should be tilted relative to the plane of the rest of the solar system. The long axis of its orbit should point in the opposite direction from the cluster of objects it was shepherding. These were not vague qualitative claims. They were numbers, angles, distances, things you could test once the right telescope was pointed at the right part of the sky. What made the 2016 paper land as hard as it did was partly the quality of the evidence and partly who was making the claim. Mike Brown was not a peripheral figure in Kuiper Belt science. He had discovered Eris, the dwarf planet, whose existence directly precipitated Pluto's reclassification. He had found more large Kuiper Belt objects than almost anyone alive. When Brown said he thought there was a planet out there, the field paid attention. Batygin brought the theoretical framework, the orbital mechanics, the resonance calculations. The dynamical modeling needed to show that a planet of this type could actually produce the observed clustering. Together, they made a case that was difficult to dismiss with a single objection. The collaboration between observational expertise and theoretical rigor lent extraordinary weight to their conclusion, signaling to the broader scientific community that this was not speculative astronomy, but a serious investigation grounded in rigorous mathematics and empirical data. Subsequent work strengthened the signal rather than dissolving it. Researchers added more distant Kuiper Belt objects to the sample as surveys pushed to greater depths. A meaningful fraction of the newly discovered objects fell into the same clustering pattern. A 2021 analysis that incorporated additional objects found the alignment persisted even after attempting to account for potential biases in where surveys had been looking. The orbital plane of the distant Kuiper Belt, in the region where Planet 9's influence should be strongest, appeared to be measurably tilted relative to the plane of the inner solar system. The tilt was subtle, but it matched the prediction. This was not supposed to happen without a cause. None of this constitutes proof. Batygin and Brown never claimed it did. What they claimed was that the simplest explanation for everything they were seeing, the perihelion clustering, the tilt of the orbital planes, the existence of objects in orbits that standard models have difficulty producing, was a single large, unseen body orbiting at extreme distance. Not a cloud of small objects, not an unusual distribution of random noise, but one planet pulling on everything around it with the patient consistency of gravity operating over billions of years. The clustering was not just a curiosity, it was a fingerprint. Batygin and Brown believed they knew what had pressed it into the data. If Planet 9 exists, it is nothing like any world in the familiar solar system. The planets most people can name, Mercury, Venus, Mars, Jupiter, are objects you can find in a basic textbook. Their masses, orbits, and compositions have been measured with precision. They are known quantities. Planet 9, if it is real, belongs to a completely different category. It is an ice giant, something closer in nature to Uranus or Neptune than to anything in the inner solar system. That means a world built mostly from water, methane, and ammonia in frozen and compressed forms, wrapped around a rocky core, shrouded in a thick envelope of hydrogen and helium gas. Not a rocky planet you could stand on, not a gas giant the size of Jupiter. Something in between, massive enough to be unambiguously a planet, strange enough to feel alien compared to every world we have ever visited. The mass estimates sit between 5 and 10 times the mass of Earth. That range matters. At 5 Earth masses, Planet 9 would be one of the smaller ice giants imaginable. At 10, it would be approaching a third the mass of Uranus. Either way, it would contain roughly 5,000 times the mass of Pluto. This is worth holding on to for a moment. The debate over Pluto's planetary status consumed years of headlines and public argument. Planet 9 would make that debate look almost quaint. There is no version of planetary definition under which an object this massive gets demoted to anything smaller than a full planet. It would gravitationally dominate a region of space larger than the sphere of influence of any planet currently on the books. Neptune controls a substantial gravitational neighborhood. Planet 9's would dwarf it. The orbit is where things become almost hard to picture. Planet 9 is not proposed to sit at a fixed, comfortable distance from the Sun. Its path would be an enormous ellipse, stretched to extremes that have no parallel among the known planets. At its closest approach, what astronomers call perihelion, it might come within a few hundred astronomical units of the Sun. At its farthest point, it could swing out beyond 1,000 astronomical units. For reference, Neptune orbits at roughly 30 astronomical units. Pluto reaches about 49 astronomical units at its farthest. The inner edge of the proposed Planet 9 orbit is already 10 times farther than that. The outer edge is territory that has essentially never appeared on any map of the solar system that meant anything. An orbit this large takes time, a long time. The estimated orbital period for Planet 9 falls somewhere between 10,000 and 20,000 Earth years. One circuit of the Sun takes longer than recorded human civilization has existed, multiplied several times over. This is why no survey has caught it moving. Detecting a planet requires seeing it shift position against the background stars. Planet 9 moves so slowly that across an entire human lifetime of observation, across all of recorded telescopic astronomy, it would have covered only a tiny arc of its full path. Traditional sky surveys, designed to catch fast-moving nearby objects, or distant but predictable ones, were never built to find something this slow at this distance. The faintness is the other wall. At distances between 400 and 800 astronomical units, where Planet 9 is most likely to be sitting right now, statistically, sunlight has spread so thin that even a world the size of a small ice giant reflects almost nothing back toward us. The brightness of a planet depends on how much sunlight reaches it and how much it reflects. Sunlight falls off with the square of distance. At 500 astronomical units, a planet receives about 250,000 times less sunlight than Earth does. What little it reflects, then, has to travel that same enormous distance back. The result is a point of light so faint that most of the telescopes that have swept the sky for the past 2 centuries were not sensitive enough to detect it, even if they had been pointed directly at it. This is not a failure of diligence. T is a physics problem. The signal was below the noise floor of everything we had. Here is the strange thing. We have surveyed large fractions of the sky. Generations of astronomers have pointed powerful instruments outward and catalogued what they found. And yet a planet 10 times the mass of Earth could have been sitting in our own solar system this entire time, undetected, because the distance makes it nearly invisible, and its motion makes it nearly indistinguishable from a background star on any single night of observation. The night sky does not give up objects like this easily. Some researchers have gone further and asked where Planet 9 actually came from. One theory is that it formed in the inner solar system, alongside Jupiter, Saturn, Uranus, and Neptune, in the chaotic first 100 million years of the solar system's history. The early solar system was not the orderly arrangement it resembles today. Giant planets were migrating. Their gravitational interactions were violent and unpredictable. Smaller protoplanets forming in that environment could be flung outward by a close encounter with Jupiter or Saturn, sent onto wide, elongated orbits that carried them to the extreme outer solar system. If one of those ejected bodies was massive enough, it could have settled into a stable long-period orbit rather than being thrown out of the solar system entirely. Planet 9, under this scenario, is not a foreign object captured from another star. It is a native of the early solar system that got lost in its own backyard and has been orbiting in the dark ever since. Other researchers have proposed that Planet 9 might be a captured planet, a world born around another star and grabbed by the Sun's gravity during the period when the Sun was still embedded in its birth cluster, surrounded by other young stars at relatively close range. Captured planets are not impossible. The dynamics of a star cluster can result in objects exchanging between systems. Whether this explains Planet 9 specifically is harder to say, but it is not ruled out. What is clear is that nothing about this object, if it exists, is small or ambiguous. The object at the center of this hypothesis is not some small borderline body. It would be one of the dominant gravitational players in the outer solar system, and its absence from our catalogues after centuries of sky watching is either an extraordinary oversight or a sign that the hypothesis is wrong. The orbital clustering at the heart of the Planet 9 hypothesis is not something you can see by looking at a picture of the solar system. It lives in the numbers. Specifically, it lives in the angles, the orientations of orbits when you plot them mathematically, and ask whether they are pointing in random directions or whether something has quietly pushed them into alignment. When Battergin and Brown ran those numbers in 2016, what they found was not subtle. 6 distant Kuiper Belt objects were clustered in physical space in a way that had roughly a 1 in 15,000 chance of being a coincidence. The question was, what caused it? And the mechanism they proposed has a name: secular resonance. Secular resonance is one of the slower, quieter forces in gravitational physics. But over enough time, it is extraordinarily powerful. When a massive planet orbits in a distant elongated path, it does not simply pass by smaller objects and leave them undisturbed. Its gravity tugs on them with every orbit. Because the geometry is never quite the same twice, those tugs accumulate. Over millions of years, the planet gradually herds the orbital orientations of nearby small bodies. Pulling their closest approach points toward a preferred direction and tilting their orbital planes into alignment. The process is slow enough that you would never notice it on a human timescale. But the solar system is 4.5 billion years old. Secular resonance has had time to work. We already know this mechanism is real because we have been watching it operate for decades. Neptune does exactly this to Pluto. It does it to an entire population of Kuiper Belt objects called the Plutinos. Objects locked into a 2 to 3 orbital resonance with Neptune, where they complete 2 orbits for every 3 Neptune completes. Neptune's gravity has shaped those objects' orbits over billions of years, herding them into predictable configurations that astronomers understand well enough to use as a calibration tool. The physics is not exotic. It is the same gravitational machinery that organizes ring structures around Saturn and shepherds asteroids in the inner solar system. What Battergin and Brown proposed is that a more distant and more massive planet is doing the same thing on a larger scale, over longer timescales, to the most remote objects we can detect. The specific signature they identified was twofold. First, the 6 clustered objects all had their perihelion points, their closest approach to the Sun, oriented in roughly the same direction. Statistically, those should be scattered randomly around the sky. They were not. Second, the orbital planes of those objects were all tilted in a consistent way relative to the plane of the solar system. Again, that kind of coherence does not arise by chance. A planet in a specific distant orbit, they calculated, could produce both effects simultaneously. The clustering was not just an interesting pattern, it was a prediction, because it told you where the perturbing planet had to be. The years after 2016 brought more objects and more scrutiny. A 2021 analysis by Batygin and collaborators incorporated a larger sample of distant Kuiper Belt objects and found that the clustering signal did not weaken. It persisted. In some respects, it strengthened. Objects discovered by surveys that had not been used in the original 2016 study showed the same orientation patterns. The predicted tilt of the average orbital plane of the Kuiper Belt in the region where Planet 9's influence should dominate was compared against actual observations of that plane. The match was close enough to be notable. The tilt is small, a few degrees, but it falls right where the model says it should fall. Here is something worth holding on to. The Planet 9 hypothesis is not simply a claim that an unseen planet exists. It is a claim that a specific planet, with a specific mass and orbit, is producing a specific, measurable gravitational effect on specific objects. That level of precision makes it testable in a way that vague hypotheses are not. Either the predictions match the data or they do not. So far, for the objects in the original sample, and for many of the objects added since, they match. But there is a serious objection, and honest science requires taking it seriously. Almost every one of the objects showing the clustering signature was discovered by surveys that did not cover the full sky evenly. They were concentrated in certain regions, particularly away from the dense star fields of the galactic plane, where faint objects are easier to detect. If most of the known extreme Kuiper Belt objects were found in overlapping patches of sky, then their orbital orientations might cluster simply because of where the telescopes were pointed, not because any planet herded them. This is the observational bias argument, and it is not a fringe objection. It was published in peer-reviewed studies by researchers who ran careful statistical tests and concluded that the clustering could plausibly be explained without any hidden planet. The response from Planet 9 proponents has been to model the bias explicitly. They built simulations that accounted for where each survey looked, then asked whether the clustering survived after correcting for it. Their conclusion was that it did, that the bias alone was insufficient to produce the pattern. Critics pushed back on the assumptions built into those corrections. The debate has continued in exactly that form, each side refining the analysis, each side finding the result that its model predicts. Neither has produced evidence clean enough to end the argument. What the field genuinely needs is a sample of extreme Kuiper Belt objects discovered by a survey that covered the entire sky uniformly, with no preferred direction, no gaps, no detection biases that favor one orbital orientation over another. With a sample like that, you could measure the clustering directly and know whether it reflects physical reality or telescope geometry. That survey does not exist yet. The debate over whether the clustering is real or an artifact of survey bias is the central unresolved tension in Planet 9 research. It is the question that the next generation of observations is specifically designed to settle. The Planet 9 hypothesis is the most famous version of the hidden planet idea, but it is not the only one with serious scientific backing. While Battergin and Brown were building their case for a distant ice giant 10 times the mass of Earth, a separate line of research was pointing towards something different, smaller, closer, and in some ways harder to dismiss. Patrick Likavka, an astronomer at Kindai University in Japan, has spent years analyzing the orbital structure of the Kuiper Belt from a different angle. What he found does not require a world the size of Neptune sitting 1,000 astronomical units away. His proposed planet, sometimes called the Kuiper Belt planet, sometimes Planet Y, would have a mass somewhere between 1.5 and 3 times that of Earth. Its orbit would place it at roughly 200 to 500 astronomical units from the Sun. That is still an extraordinary distance. Neptune sits at only 30 astronomical units, and even Pluto rarely ventures past 50. But compared to the proposed location of Planet 9, this is practically next door. The distinction matters. Planet 9, if it exists, is extreme in almost every sense. It would be massive, unimaginably remote, sitting in an orbit so elongated that its period might span tens of thousands of years. To explain why it hasn't been found, you have to pile up reasons. Its vast distance, its slow motion across the sky, the fraction of its orbit spent at maximum separation from the Sun. Each reason is legitimate, but the cumulative weight of them starts to feel like special pleading. Planet Y requires far less of that. A smaller body at closer range should reflect more detectable light, move more quickly against the background of stars. In principle, show up in a well-designed sky survey far sooner. What Likavka's model is specifically trying to explain are several features of the Kuiper Belt that standard formation theory handles poorly. The Kuiper Cliff is one of them. That abrupt drop-off in the number of objects beyond 50 astronomical units has never been cleanly reproduced in simulations that include only the 4 known giant planets. Something seems to have swept that region, or sculpted its outer boundary with a precision that random physical processes don't naturally produce. A planet orbiting in the 200 to 500 astronomical units range could, over the age of the solar system, have exerted exactly the kind of gradual gravitational influence needed to thin out that population and sharpen that edge. There is also the question of certain resonant objects, bodies in the Kuiper Belt, whose orbits are locked into specific mathematical ratios with Neptune's orbital period. The distribution of these objects doesn't quite match what models predict. Some of them are in configurations that are stable today, but are difficult to produce in simulations without invoking an additional gravitational influence somewhere in the outer system. A moderate-sized planet at the distances Likavka proposes could have nudged these objects into their current configurations during the early, chaotic period of solar system history. And unlike some of the orbital fingerprints attributed to Planet 9, these features have been noted in populations that are large enough to carry reasonable statistical weight. Here is the strange thing about Planet Y's absence from our catalogues. Even at 200 astronomical units, the closer end of its proposed range, an Earth mass object receives so little sunlight that its reflected brightness would be almost undetectable to most telescopes that have ever been pointed at the sky. It would appear to move slowly against background stars, though faster than Planet 9 would. Its predicted location is not a broad swath of the sky, but a more targeted region based on the orbital mechanics of the objects it's supposed to be influencing. That targeted prediction is both an advantage and a limitation. It means the search is more focused. But it also means that if the predicted location is wrong by even a moderate amount, decades of sky surveys could have swept past it without noticing. What makes this period of Kuiper Belt research genuinely unusual is that two distinct planet hypotheses, proposing objects of very different character in different parts of the outer solar system, are both considered scientifically credible at the same time. They are not simply variations on the same idea. Planet 9 is a massive ice giant in an extreme elongated orbit, proposed to explain a clustering pattern in the most distant Kuiper Belt objects. Planet Y is a much smaller body in a more modest, though still remote, orbit, proposed to explain structural features in the classical and resonant belt populations. The orbital anomalies they address are not identical. It is at least theoretically possible that both objects exist, and that each one has been quietly shaping a different part of the outer solar system for billions of years. The Vera Rubin Observatory is expected to be the instrument that settles at least part of this. With a sky coverage and detection sensitivity far beyond anything previously available, Rubin should be capable of finding a Planet Y-class object within its first few years of full operations, assuming the object falls anywhere near the predicted range of distances and sky positions. Some researchers believe Planet Y is actually the easier target of the two, not because it's brighter in any absolute sense, but because its predicted location is more constrained and its distance is less extreme. If Rubin surveys the relevant region and finds nothing, that would impose very tight limits on where such a world could be hiding, may effectively rule out the hypothesis entirely. If it finds something, the decades of work building these models will have paid off in a way few outer solar system discoveries ever have. Whether Planet Y and Planet 9 are competing explanations for the same anomalies, or whether they might somehow both be real, is a question the field has not yet been able to resolve with available data. Not everyone looking at the strange orbital clustering of distant Kuiper Belt objects thinks a hidden planet is responsible. Some researchers look at the same data, the same orbital patterns, the same gravitational fingerprints, and arrive at a completely different conclusion. Not a planet, not even an unknown object, something far more fundamental. What if the problem isn't what's hiding in the outer solar system, but rather what's hiding in the equations we use to describe it? The alternative they're pointing to has a name: modified Newtonian dynamics, usually shortened to MOND. It was developed in the early 1980s by Israeli physicist Mordechai Milgram, and it was not designed with the Kuiper Belt in mind at all. Milgram was trying to solve a completely different problem. Galaxies rotate in a way that makes no sense under standard Newtonian gravity. The stars at the outer edges of galaxies move too fast. By Newton's equations, those stars should be moving slower because they're far from the gravitational center and the pull should weaken with distance. Instead, the rotation curves stay flat. Stars at the edges move roughly as fast as stars near the core. The standard explanation is dark matter, vast invisible halos of undetected mass surrounding every galaxy, providing extra gravity. MOND offers a different fix. It proposes that gravity itself behaves differently at very low accelerations. Below a certain threshold, gravity doesn't fall off quite the way Newton said. It gets a little stronger than expected. This modification is small and essentially undetectable in the kinds of gravitational environments we normally study. But at galaxy scales, and potentially at the extreme edges of a solar system, it starts to matter. Here is the thing that makes MOND relevant to the Kuiper Belt. At distances of several hundred astronomical units from the Sun, objects experience extraordinarily weak gravitational accelerations. The Sun's pull is real, but it is faint. And under MOND, at those faint acceleration levels, the gravitational influence of the broader galactic environment, specifically the stars packed into the center of the Milky Way, becomes non-negligible. In standard Newtonian gravity, that galactic pull is so small at solar system distances that it gets safely ignored. Under MOND, the calculation changes. The external gravitational field from the galaxy seeps in more effectively at the low acceleration frontier of the solar system. A pair of researchers ran this calculation and found something striking. Under MOND, those distant Kuiper Belt objects should have their orbits nudged into a preferred alignment, pulled gently by the combined gravitational influence of the galactic center, filtering through the modified equations. The clustering, in other words, comes out. Not from a hidden planet parked a few hundred astronomical units away, but from the galaxy itself acting on the outermost reaches of our solar system in a way that standard physics would never predict. The fingerprint looks similar. The orbital grouping, the preferred directions, the statistical pattern that Batygin and Brown interpreted as the work of Planet 9. MOND says all of it could be produced by galactic gravity instead. The implications of this, if it holds, are almost harder to absorb than the planet hypothesis. A hidden ice giant is an astonishing discovery, but it fits comfortably inside our current understanding of physics. It's just a planet we haven't found yet. MOND being correct is a different kind of discovery entirely. It would mean that Newton's law of gravitation, which has been working flawlessly for 3 centuries across every test we've applied it to within the solar system, has a blind spot. It behaves differently in a regime of very low acceleration that we haven't been able to probe carefully from here. That is not a small revision. Most astronomers remain deeply skeptical, and there are real reasons for that skepticism. MOND has a complicated history. It works remarkably well for certain galaxy rotation problems, but it has a much harder time with other observations, particularly galaxy clusters, where dark matter models outperform it substantially. Within the solar system itself, MOND has produced predictions that don't sit cleanly with what we observe. The Pioneer anomaly, an unexplained drift in the trajectories of the Pioneer spacecraft that was once thought to be a candidate for MOND effects, turned out to be explained entirely by heat radiation from the spacecraft's own power systems. MOND didn't predict that outcome, and it didn't explain away the anomaly either. There's also a more specific problem. The orbital clustering of distant Kuiper Belt objects is a very precise signal. It has particular statistical properties, particular orbital geometries, particular preferred directions. Getting all of that right from a galactic tidal effect under MOND is genuinely difficult. The galactic gravity hypothesis has to reproduce the specifics, not just the general tendency toward alignment. So far, that case has not been made convincingly enough to move most of the community. The Planet 9 interpretation still commands more support, precisely because a gravitationally dominant nearby body is a cleaner, more targeted explanation for a clean and targeted signal. But dismissing MOND entirely because it's inconvenient would be its own kind of error. The theory has survived longer than many of its critics predicted. It keeps finding corners of observational data where it performs better than it should if it were simply wrong. And the galactic tidal effect on the outer solar system is a real physical mechanism, even in standard gravity. MOND simply makes it stronger. The possibility that the signal astronomers are reading as a planet might actually be written by the gravity of the entire Milky Way is exactly the kind of uncomfortable alternative that good science cannot simply dismiss. On a ridge in the Chilean Atacama Desert, a telescope unlike anything previously built in the history of astronomy is currently working its way through the first year of a 10-year survey of the sky. It is called the Vera Rubin Observatory, named for the astronomer who spent decades demonstrating that galaxies contain far more mass than anyone could see. The choice of name is appropriate. Rubin spent her career proving that the universe hides things in plain sight. The telescope bearing her name was built, in no small part, to do exactly the same work. Most telescopes operate like detectives chasing specific suspects. You identify a target, you point the instrument, you collect light from that one object for as long as you need. The Vera Rubin Observatory does not work that way. Its survey strategy is closer to a dragnet than an investigation. Every few nights, it images the entire accessible sky. Then it does it again and again. Over a decade of operations, it will build up a massive, repeated record of the sky so complete that anything that moves, brightens, dims, or appears where it wasn't before will be caught. There is no hiding from a telescope that sees everything, repeatedly, for 10 years straight. The engineering behind this is worth holding in your mind for a moment. The primary mirror is 8.4 meters across. That is large by any measure, though there are bigger mirrors in the world. What makes Rubin genuinely unprecedented is its camera. It carries the largest digital camera ever built for astronomy, capable of capturing an image covering roughly 40 times the area of the full moon in a single exposure. Most wide-field cameras in astronomy sacrifice depth for breadth, catching only the brightest objects across a wide patch of sky. Rubin is deep enough to detect objects that would be invisible to previous survey instruments, while still covering the entire sky on a cadence of days. That combination has never existed before. For Kuiper Belt science, the implications are almost difficult to overstate. Right now, after 30 years of searching with every instrument available, astronomers have catalogued roughly 3,000 to 4,000 Kuiper Belt objects. Rubin is expected to discover around 35,000 in its first few years alone. That is not an incremental improvement. It is a transformation. The known population of the outer solar system is about to grow by nearly a factor of 10, and most of those new objects will be found in the first year or two of the survey, not the last. What does that mean for the Planet 9 debate? It means the argument that has been standing in the middle of this problem since 2016 is about to become answerable. The central weakness in the orbital clustering evidence has always been the same. The objects showing strange alignment were all discovered by surveys that covered limited and specific patches of sky. If the surveys were biased towards certain directions, the clustering they found could be an artifact of where the telescopes were pointed, rather than a genuine physical signal. Critics have made this argument for nearly a decade. and supporters of the Planet 9 hypothesis have never been able to fully refute it with existing data. The datasets were simply too small, too patchy, and too shaped by the biases of particular instruments and observing programs. Rubin changes this entirely. A full-sky survey, repeated systematically over years, does not have the same directional biases as targeted observing campaigns. When Rubin has added tens of thousands of new Kuiper Belt objects to the catalogue, and when researchers run the clustering analysis on that full, unbiased sample, the answer will be clear. Either the clustering is real and shows up in the complete dataset, stronger and cleaner than before, or it dissolves into noise when the gaps in the older surveys are filled in. There is no middle ground here. The statistics, with 35,000 objects instead of a few dozen, will be overwhelming either way. Beyond clustering, Rubin will systematically address the extended belt. The population of objects sitting at 70 to 90 astronomical units from the Sun, detected in hints by the Subaru telescope survey, needs confirmation. Finding those distant objects is genuinely hard. They are faint. They move slowly. You need deep imaging and long baselines to distinguish them from background stars. Rubin was not designed specifically for this problem, but it is exactly the kind of instrument that solves it anyway. Repeatedly imaging the sky to great depth, it will catch distant objects moving incrementally from frame to frame across months and years of observations. If a second population of Kuiper Belt objects really does exist at 70 to 90 astronomical units, Rubin will map it. If the apparent detection was a statistical fluke, Rubin will reveal that too. There is something almost strange about having the answer this close. Astronomers have been arguing about Planet 9 for nearly a decade. They argued about whether the clustering was real. They argued about the mass and the orbit and the distance. They proposed MOND as an alternative and debated that. The field has spent years in a kind of productive uncertainty, generating hypotheses faster than the data could test them. Rubin is the data catching up. Researchers have been specific about the timeline. Within its first year of scientific operations, Rubin should have enough new Kuiper Belt detections to begin running meaningful clustering tests. Within 2 years, the results should be unambiguous. The team members who have been working on Planet 9 the longest are on record saying that Rubin will either find the planet or definitively rule it out. Not narrow the range, not strengthen the evidence, settle it. That is a rare thing for a scientist to say, and the fact that they are saying it reflects how thoroughly Rubin's survey design addresses the specific weaknesses that have kept the debate alive. The Atacama is one of the driest places on Earth, which is why astronomers build there. Clear skies, minimal atmospheric distortion, almost no light pollution. A decade from now, the dataset that Rubin accumulates on that ridge will be one of the most scientifically valuable records of the sky ever assembled. Within a year or two of its first data release, the Vera Rubin Observatory is expected to do something no previous instrument has managed. Either find Planet 9 or prove conclusively that it is not where the models say it should be. A surprising fraction of Kuiper Belt objects are not alone. When astronomers began cataloguing the Kuiper Belt in earnest after 1992, they expected to find a collection of solitary frozen bodies drifting in the dark on independent orbits. What they found instead, as the surveys deepened and the instruments improved, was something harder to explain. Roughly a third of the cold classical Kuiper Belt objects, the quieter, more circular population that sits near the heart of the belt appear to have companions, not moons in the traditional sense, true binary partners, two roughly equal-sized bodies orbiting each other as they move together through the outer solar system. This is strange. In the inner solar system, among the rocky asteroids and the near-Earth population, binaries exist, but they are relatively rare. The Kuiper Belt's binary fraction is much higher, and in the cold classical population, it is higher still. That difference is a clue. It suggests that whatever process formed the cold classical objects was fundamentally different from what built the rocks closer to the Sun. Different enough to leave paired systems behind at a rate that is almost impossible to explain through random chance alone. Here is what a binary KBO actually looks like. Two objects, often within a factor of 2 of each other in size, separated by distances that can range from a few hundred to several thousand kilometers. They orbit their common center of mass on timescales of days to months. At the distances of the Kuiper Belt, this pairing is stable. There is nothing nearby to disrupt it. The Sun's gravity is weak at 40 or 50 astronomical units. Encounters with other large bodies are rare, so once a binary forms out there, it tends to stay a binary. This is part of why so many survived. The outer solar system is a quiet neighborhood, and quiet neighborhoods preserve things. What caused them to form in pairs in the first place is where the science gets genuinely interesting. For a long time, the default assumption was collisions. Small bodies in the early solar system collided constantly. They stuck together, broke apart, and slowly built up larger objects through a process called accretion. In this model, a binary would form when a collision produced a loosely bound pair rather than a single merged body. It is a reasonable picture, and it works reasonably well for populations closer to the Sun. For the Kuiper Belt, though, it runs into trouble immediately. The cold classical objects are too numerous, too similarly sized, and paired too often for collisions to explain them cleanly. The math does not come out right. The competing idea is called the streaming instability. The concept is worth holding in mind because it changes the whole picture of how the outer solar system was built. In the early solar nebula, the disk of gas and dust surrounding the young Sun was not uniform. Aerodynamic drag caused small solid particles to drift inward and concentrate into dense filaments and clumps. At a certain density, a clump could become gravitationally self-bound. It would stop drifting and begin to collapse under its own weight, directly forming a solid body without any need for collisions to build it up piece by piece. This is the streaming instability, and critically, when researchers model this collapse in detail, the most common outcome is not a single object, it is two. The collapsing clump tends to frag, melt and form a bound pair almost naturally because the angular momentum of the infalling material does not permit a clean single-body collapse. Pairs are the path of least resistance. Triplets also appear in the simulations, though less frequently. This means the binary systems scattered across the cold classical Kuiper Belt are not accidents. They are the default product of the formation mechanism. They are what you expect to find if the streaming instability is correct. Each binary pair is, in a very literal sense, a fossil from the moment of formation. The two components formed together from the same collapsing cloud of material in the same instant roughly 4.5 billion years ago. They have been orbiting each other ever since, The discovery of triple systems pushed this further. A triple system in the Kuiper Belt is exactly what it sounds like. 3 objects gravitationally bound to one another. The first confirmed triple was already remarkable. Then a second candidate emerged. A binary that had been catalogued as a simple 2-body system showed subtle irregularities in how its components moved. When the orbital dynamics were worked through carefully, the only clean explanation was a third body tucked in close to one of the existing pair. Too close to be resolved directly by telescope imagery, but detectable through its gravitational effect on the orbits it shared. The inference from orbital behavior, rather than direct detection, is the same method used to find exoplanets. Something is there. We can see what it is, doing even when we cannot see it. The existence of multiple triple systems immediately raises a statistical point that is almost uncomfortable. If we have found 2, and one of them was only detectable through indirect methods, how many are we simply missing? The Kuiper Belt is far enough away that resolving close companions requires ideal conditions. Systems where the third body orbits within a few hundred kilometers of its partner would be effectively invisible to current survey instruments. The true triple fraction could be substantially higher than what the catalogues show, hidden not because triples are rare, but because they are compact. For the formation models, this matters enormously. The streaming instability scenario handles binaries and triples naturally, because the gravitational collapse of a rotating clump of material tends to fragment at multiple scales. The collision-based accretion model struggles to produce them at the observed rates, because getting 2 bodies to end up in a stable mutual orbit through a random collision requires a very narrow range of impact parameters. Producing triples through collisions requires threading an even narrower needle. The numbers simply favor gravitational collapse. The streaming instability passes this test in a way that sequential accretion does not. The existence of these multiple systems is not a footnote in Kuiper Belt science. It is one of the cleanest windows into how the outer solar system was actually assembled from the raw materials of the early solar nebula. In January of 2024, a small team of Japanese astronomers set up telescopes at multiple locations across Japan and waited for a frozen rock the size of a small country to pass in front of a distant star. The object they were watching is called 2002 X593. It is not famous. It has no dramatic backstory. It sits in a 3:2 orbital resonance with Neptune, meaning it completes exactly 2 orbits for every 3 that Neptune completes, a gravitational arrangement that keeps it locked in a predictable path through the outer solar system. Its diameter is roughly 500 kilometers. That sounds large until you remember that Earth's moon is about 3,500 kilometers across. In the Kuiper Belt, 500 kilometers is ordinary. There are hundreds of objects in this size range. Nothing about 2002 X593 had ever given astronomers a reason to treat it differently from any of them. What made January of 2024 special was geometry. The object was going to pass directly in front of a bright background star as seen from Japan, an event astronomers call a stellar occultation. These alignments are rare. The window of opportunity is brief. The shadow of the object sweeps across Earth's surface at the same speed the object is moving relative to the star, and if you are not in the right place at the right moment, you miss it entirely. Ko Arimatsu and his team had calculated where the shadow would fall. They positioned themselves accordingly. spread across multiple sites to maximize the chances of a clean detection. Then they waited. Here is what a stellar occultation actually tells you. As the object drifts in front of the star's light drops. If the object has no atmosphere, the drop is sharp and abrupt. The star simply vanishes the instant the solid body eclipses it, and reappears just as suddenly when the body passes. The edges of the dimming curve are clean. What you get is a precise measurement of the object's size and shape. Astronomers have used this technique for decades, and for airless Kuiper Belt objects, it almost always produces exactly this kind of clean, hard-edged signal. An atmosphere changes everything. Gas bends light. When starlight passes through the edge of an atmosphere before the solid body blocks it entirely, the atmosphere refracts the beam, scattering it, dimming it gradually rather than cutting it off. The star does not simply vanish, it fades. The curve goes soft at the edges. The shape of that softness tells you how thick the atmosphere is, how it is structured, and roughly what it is made of. Every planetary atmosphere in the solar system with confirmed structure has been measured this way at some point. The gradual dimming profile is the signature of something gaseous. There is no other explanation for it. When Arimatsu's team processed their data from January 2024, the curve was not clean. The star faded. Gradually, the edges were soft in a way that an airless 500-kilometer rock has no business producing. The team checked their instruments. They checked the reduction pipeline. The signal was real. 2002 XV93 had an atmosphere. That result was almost too strange to accept immediately. Pluto has an atmosphere, and Pluto is large enough and cold enough that nitrogen gas can persist at its surface without escaping into space at significant rates. Pluto is also in a special situation. It gets slightly closer to the Sun on part of its orbit, enough to sublimate surface ices and temporarily thicken its atmospheric envelope. Pluto is the exception. The expectation was that Pluto would remain the exception for a long time, perhaps forever, among small Kuiper Belt objects. 2002 XV93 is not Pluto. Its surface gravity is a small fraction of Pluto's. At 500 kilometers across, the object barely holds itself into a sphere. The gravitational pull at its surface is so weak that a person standing on it could throw a ball into orbit. Under standard models of atmospheric physics, any volatile gas that sublimates off its surface should escape almost immediately. The atmosphere should not be there. The textbook answer was clear, and the data was contradicting it. Two explanations emerged, and neither is comfortable. The first is that the models of atmospheric retention for small, cold bodies are wrong in some important way. Maybe at the temperatures and pressures relevant to the outer Kuiper Belt, gases behave differently than the standard equations predict. Maybe there are condensation and cold trapping effects that slow the loss of volatiles in ways that have not been properly accounted for. If this is right, other small Kuiper Belt objects might have thin atmospheres that we have simply never had the geometry to detect. The catalogue of bodies considered airless might need to be revisited. The second explanation is more dramatic. Maybe 2002 XV93 is actively producing its atmosphere right now. Something on or beneath its surface could be venting gas, sublimating ices exposed by a recent impact, or outgassing from an interior that is warmer than it should be. If the atmosphere is being actively replenished, the object is not geologically dead. It is doing something. the frozen outer solar system, which astronomers have described for decades as inert and unchanging, would be harboring active processes in at least some of its smaller members. Neither possibility was predicted. Both have serious implications for how we think about the Kuiper Belt as a whole. If even a 500-kilometer body in the cold dark beyond Neptune can hold gas against the vacuum of space, then the outer solar system is a fundamentally more complicated environment than the models have been treating it as. The discovery did not come with a clean resolution. Arimatsu and his team identified the atmosphere and laid out the plausible explanations, but distinguishing between them requires follow-up observations that have not yet been made. What the detection made certain is that something about 2002 XV93 does not fit the standard picture. A frozen rock at those distances, at that size, was supposed to be silent. It is not. The discovery of an atmosphere on 2002 XV93 did not just add a footnote to the catalogue of known KBOs, it suggested that the outer solar system was considerably more active than the standard models had any room to accommodate. For most of the time, astronomers have known about it. The Kuiper Belt has been described the same way: a cold, dark, largely static collection of frozen leftovers from the solar system's formation. That description made sense. At 40 to 50 astronomical units from the Sun, temperatures hover around -220 degrees Celsius. Sunlight arrives so faint, it would look like little more than a bright star. There is no meaningful solar heating at those distances. Nothing to drive weather, nothing to crack ice sheets, nothing to push material around. For billions of years, the picture was of objects sitting unchanged in the dark, essentially frozen in place since the solar system was young. The textbook version of the Kuiper Belt was a graveyard, quiet, cold, and finished. That picture has been breaking apart. In 2024, researchers using the James Webb Space Telescope pointed at two of the largest known dwarf planets in the Kuiper Belt, Eris and Makemake, and found something that did not fit the graveyard model. The data suggested both bodies might be showing signs of internal geological activity, not dramatic activity, not volcanoes visible from orbit, but chemical signatures and surface features that, under careful analysis, hinted at processes still unfolding beneath the surface. Possibly, in both cases, liquid water. That last part is worth sitting with. Liquid water in the outer Kuiper Belt. The reason this is surprising has everything to do with where the heat would come from. Solar energy is essentially useless at these distances, so any internal activity has to be powered from within. For objects the size of Eris and Makemake, both roughly 2/3 the diameter of Pluto, the most plausible internal heat source is radiogenic decay. Certain isotopes of uranium, thorium, and potassium embedded in the rocky interiors of these bodies have been slowly releasing heat for 4.6 billion years, the way a faintly warm stone holds heat long after a fire has gone out. Under the right conditions, that steady trickle of heat, sustained over geological timescales, could be enough to maintain a layer of liquid water deep beneath a frozen shell. That is the hypothesis. It is not proven, but it is not absurd. Not everyone in the field is convinced the evidence is there yet. Mike Brown, a professor of planetary astronomy at the California Institute of Technology, and one of the people who knows Kuiper Belt objects as well as anyone alive, has been direct about his skepticism. Everybody wants these things to be geologically active, he has said. They might be. But the evidence, in his view, is sparse, and he is not wrong to be cautious. What Webb detected are indirect signals, spectroscopic signatures that suggest certain chemical compositions, features that could be explained by internal processes, but could also be explained by other things. To know for certain, you would need to go there. A spacecraft in orbit around Eris or Makemake, with instruments designed to look for tidal flexing, thermal gradients, or direct signs of subsurface liquid, would answer the question definitively. No telescope on Earth or in low orbit can do that. What makes the debate harder to set aside is what came before this. The atmosphere detected on 2002 XV93 was not expected either. That object is far smaller than Eris or Makemake, small enough that its surface gravity should have been completely incapable of holding on to any kind of volatile atmosphere over geological time. Yet the stellar occultation data from January 2024 was unambiguous. Something was refracting starlight around that object. Something was there. The leading explanation involves recent activity, outgassing, the release of volatiles from the surface or just below it, triggered by processes that are still being worked out. The Kuiper Belt apparently is not as finished as it looked. What you get when you put these findings together is a different kind of place than the one in the textbooks. Not universally active, not obviously alive in any dramatic sense, but not frozen solid and geologically dead either. There is something going on out there, spread across objects of different sizes, at different distances, producing signatures that models built around cold and inert bodies were not designed to detect. The atmosphere on a small resonant object, possible subsurface liquid on dwarf planets. The emerging picture is of a belt that retained more internal energy than anyone expected, and that is still, in quiet ways, spending it. The broader implication is one that would have drawn skepticism not long ago. If subsurface oceans exist beneath Eris or Makemake, the Kuiper Belt becomes part of a longer list of places in the solar system where liquid water might exist today. That list already includes Europa, Enceladus, possibly Ganymede, possibly Titan in some form. Adding dwarf planets at 40 or 50 astronomical units extends it to distances most planetary scientists would not have seriously entertained 20 years ago. Liquid water at those distances, sustained by radioactive decay alone, surviving under a frozen lid for billions of years, is not an impossible thing. It is just a thing we were not looking for, and therefore did not find. A dedicated mission would change everything. A spacecraft sent to orbit Eris, built to measure gravitational anomalies that would reveal internal density variations, equipped with instruments to track tidal deformation, would settle the subsurface ocean question within a few years of arrival. No such mission is currently funded. The travel time alone would be measured in decades with existing propulsion technology. But the science case is building, and the case is being made in large part because of what the last few years of telescope data have started suggesting. The Kuiper Belt, it is becoming clear, is not the solar system's attic. It is something considerably more complicated and possibly considerably more alive. The Kuiper Belt began as something far more violent than the frozen quiet it presents today. 4.5 billion years ago, there was no belt. There was a disk, a vast churning ring of gas, dust, ice stretching far beyond where Neptune now sits, carrying somewhere between 7 and 10 times the mass of the entire Earth. What exists out there today is a remnant. a thin shadow of what was once an enormous reservoir of raw planetary material. Understanding how that transformation happened is one of the harder problems in planetary science. The leading answer is a story about a solar system that rearranged itself so violently that most of what it started with simply ceased to exist. The dominant framework for this story has a name. Scientists call it the Nice Model, after the city in France where it was first assembled by a group of researchers in the early 2000s. The core idea is striking. In the early solar system, the four giant planets, Jupiter, Saturn, Uranus, Neptune, were not where they sit today. They orbited closer together, closer to the Sun, on paths that were more circular and more compact than their current trajectories suggest. The outer disk of planetesimals extended well beyond them. For a time, this arrangement held a fragile stability. Then something shifted. The trigger was a gravitational interaction between Jupiter and Saturn. As these two giants slowly drifted into a specific resonance with each other, their combined gravitational influence destabilized the entire outer system. The ice giants, Uranus and Neptune, were flung outward. Neptune in particular migrated dramatically, plowing through the outer disk like a wave moving through shallow water. Every small body in its path faced a choice it did not get to make. Some were pushed inward, toward the inner solar system. Some were flung entirely out of the solar system, lost to interstellar space. A smaller fraction survived in the chaotic wake Neptune left behind. That surviving population is the Kuiper Belt. The Nice model's predictive power is genuinely impressive. It explains the late heavy bombardment, that period roughly 4 billion years ago when the inner solar system, including the Moon and early Earth, was pelted with an intense wave of impactors. The model's dynamics naturally produce exactly that kind of inward surge when the giant planets shift. It also explains how Jupiter captured its Trojan asteroids. The large swarms of objects locked into gravitational equilibrium ahead of and behind the planet in its orbit. Those captures require a specific dynamical window that opens and closes during Neptune's migration. The Nice model produces that window cleanly. The broad shape of the Kuiper Belt, its extent, its general population of objects in resonance with Neptune, also emerges from the model without forcing. This is what makes the gaps so uncomfortable. A model this successful at explaining some things should not fail as conspicuously as the Nice model fails at explaining others. And it does fail. The distribution of classical Kuiper Belt objects, the ones sitting in roughly circular orbits, not locked into resonances with Neptune, does not quite match what the model produces. The actual population is divided into what astronomers call the cold classical and hot classical populations. Objects with very different inclinations and orbital histories sitting in the same general region. The model can produce something like this division, but not with the exact proportions and orbital characteristics that observations show. There is a mismatch that has resisted clean resolution for 2 decades. The Kuiper Cliff sits at the same problem from a different angle. The Nice model predicts a gradual thinning of the population beyond 50 astronomical units, perhaps with some complicated structure. What astronomers actually see is a sharp, cliff-like drop in the number of objects at that boundary. The model has no clean mechanism for producing an edge that abrupt. Attempts to explain it by adjusting Neptune's migration speed or the initial mass profile of the disk have produced results that improve the fit but never nail it. The mass problem is possibly the most sobering of all. The primordial disk contained, by most estimates, 7 to 10 Earth masses of material. The Kuiper Belt today holds a small fraction of 1 Earth mass. The NICE model absolutely predicts massive loss. Neptune scattering most of the disk population is the whole point of the model. But getting the loss to produce the right final mass with the right distribution of orbital properties is genuinely hard. You can run simulations that deplete the disk appropriately, or you can run simulations that get the orbital distribution roughly right. Getting both at the same time, consistently, has proven frustratingly difficult. Something about the depletion process isn't fully captured by the model. Then there are the inclination and eccentricity distributions. Specific populations of Kuiper Belt objects have orbital tilts and shapes that the NICE model, even in its most refined versions, struggles to reproduce. Some objects are inclined too steeply. Some resonant populations have eccentricities that don't match the predicted outputs. Each of these discrepancies is individually small enough to explain away. Together, they form a pattern suggesting that the model is missing something important about what happened in the outer solar system. What that something is remains genuinely open. Some researchers argue that the early solar system suffered additional disturbances beyond what the NICE model includes. A close passage by a neighboring star in the Sun's birth cluster, perhaps, or a second gravitational instability that the model doesn't account for. Others argue that the NICE model's initial conditions are wrong, that the giant planets started in different positions or with different mass distributions than assumed. A few researchers have argued that an additional planet, something that was later lost or pushed to an extreme orbit, passed through the outer disk and did damage the model has no room for. That possibility gets its own chapter in the story of how the outer solar system was built. It is a chapter with considerably darker implications for our picture of the early solar system. What is clear is that the Kuiper Belt is not simply the quiet archive that NICE model simulations produce at the end of their runs. It has structure the model doesn't predict. It has an edge that is sharper than the dynamics allow. It has a mass budget that doesn't close without additional assumptions. Something happened out there that the best available model either glosses over or misses entirely. The observational pressure on this problem is only increasing as more distant objects are catalogued and their orbital properties measured with greater precision. The NICE model is the best story planetary scientists have for how the outer solar system was rearranged, but it is a story with missing pages. Finding those pages is one of the central projects of modern solar system research. One of the more unsettling conclusions to emerge from modern solar system dynamics is that the solar system we inhabit today is probably not the one that formed around the young sun. The NICE model, as described, gives us a reasonable account of how Jupiter and Saturn reshuffled the outer solar system and sent Neptune migrating outward through a disk of primitive material. But there is a version of those same equations that works better, produces cleaner results, matches what we actually observe in the Kuiper Belt with less leftover mess. That version requires one extra planet, an additional ice giant, roughly the size of Uranus or Neptune, that formed in the early solar system and no longer exists here, not destroyed, not quietly absorbed by another world, gone, flung out into interstellar space by a gravitational encounter so violent that the planet simply never came back. This is not a fringe idea. Some of the researchers who built the NICE model ran the simulations again and again, varying the starting conditions, looking for configurations that produce something resembling our actual solar system. What they found was that a 5-planet starting configuration, 4 giants plus 1 additional ice giant, produced more realistic outcomes than a 4-planet start. The solar system we live in, with its specific arrangement of resonances, orbital inclinations, scattered populations, fits more naturally as the survivor of a 5-body system than a 4-body one. One of those bodies lost. The mechanics of how it happened are not mysterious exactly. They are brutal. During the period of dynamical instability that the NICE model describes, the giant planets were on shifting, overlapping orbits. Close encounters between Jupiter and the smaller giants were not rare events. They were essentially inevitable. A close pass between Jupiter and an ice giant transfers an enormous amount of energy to the smaller body. If the geometry is right, the smaller planet gets kicked onto a hyperbolic trajectory, an escape path, and crosses the outer solar system at high speed, never to return. Jupiter, being vastly more massive, barely notices. The departing planet does not go quietly. On its way out, a planet-sized body moving through the outer solar system at high velocity sweeps through the region that would eventually become the Kuiper Belt and the inner Oort cloud. It scatters objects. Some get flung inward toward the inner solar system. This may be part of what drove the late heavy bombardment. That period roughly 4 billion years ago, when the Moon collected much of its crater record in a relatively short time. Others get thrown outward, seeded into the distant Oort cloud. That is itself believed to be largely composed of objects that were gravitationally scattered from the inner solar system during exactly this kind of chaos. The Oort cloud, in other words, may be a graveyard for material that an ejected planet scattered on its way out the door. The traces of this event should still be readable, at least in principle, in the orbital distribution of small bodies in the outer solar system. The problem is that reading them requires knowing what the starting conditions were, how many planets, in what orbits, with what masses, and those starting conditions are precisely what we are trying to determine. It is circular in a way that makes definitive answers genuinely hard to reach. The possibility of disturbances beyond the NICE model itself adds further complexity. The early Sun formed inside a stellar nursery, a cluster of hundreds or thousands of young stars packed into a relatively small volume of space. Close stellar encounters during this period, another star passing within a few hundred astronomical units of the Sun, could have reshaped the outer solar system in ways that left no clean record, but left real effects. Some researchers have proposed that a passing star could have tilted the early disk of planetesimals, or stripped material from the outer reaches of the solar system, or captured objects from the passing star's own disk. The Oort cloud's outer population may include objects that the Sun stole from a neighbor it spent only a few million years near. The solar system may be, in some small part, assembled from stolen parts. There's a version of this chaos that produced not one ejected giant, but 2. Some simulations produce better outcomes with 2 lost planets rather than 1. The solar system may have started with 6 giant planets. The number is uncertain because the evidence is indirect. What we know is that something extremely energetic happened in the outer solar system early in its history. The Kuiper Belt carries the record of that event in the form of orbital distributions, inclinations, population gaps that our current models still struggle to fully reproduce. This is where the Planet 9 hypothesis takes on a different kind of significance. Most discussions of Planet 9 frame it as a planet we haven't found yet, something sitting quietly at 400 or 500 astronomical units, waiting to be detected. But some researchers have proposed a different origin story. If Planet 9 exists, it may not have always been that far away. It could be a surviving relic of the early chaos, a planet that came close to ejection, but not quite. Kicked onto an extreme orbit by a close encounter with Jupiter, sent to a distance of hundreds of astronomical units, but not quite given enough velocity to escape entirely. Alternatively, during the Sun's time in its birth cluster, a planet could have been captured gravitationally from another young star, pulled in by the Sun's gravity during a close stellar encounter and left in a distant, tilted orbit that matches many of Planet 9's predicted characteristics. Both possibilities are consistent with the orbital clustering evidence. Both are extraordinarily difficult to distinguish from each other with available data. The Kuiper Belt in this reading is not just a collection of icy debris. It is a detailed record of the most violent era in the solar system's history, a record that has been sitting in the outer darkness for 4 billion years, encoding the outcome of events we can barely reconstruct. The orbital distribution of Kuiper Belt objects is essentially a crime scene from the early solar system. Reading it correctly requires first knowing how many suspects were present, a number that is still being debated. Every year, observatories around the world capture infrared images of distant stars surrounded by wide, glowing rings of material that look nothing like the asteroid belt, but look remarkably like what we are finding beyond Neptune. These rings glow in infrared because they are made of dust and ice, ground down from larger bodies, heated just enough by their parent star to radiate at wavelengths our eyes cannot see. They are enormous. Some stretch out to hundreds of astronomical units from their stars. And for decades, astronomers studying them have been doing something very specific. They have been reading the gaps. When you look at one of these disks and you find a cleared zone, a ring-shaped absence of material sitting between two denser populations, the standard interpretation is almost always the same. Something is in there. A planet, or something close to it, has been orbiting through that region long enough to sweep the material out of its path, scattering smaller bodies inward or outward, leaving behind a gap with relatively clean edges. This is not speculation. It is a technique that has been used to infer the presence of planets around young stars, long before direct imaging could confirm them. The gap is the fingerprint. The planet is whoever left it. Here is the strange thing. For a long time, when astronomers compared our solar system to those disks around other stars, the comparison was unflattering. Our debris disk, the Kuiper Belt, looked small. It appeared to cut off around 50 astronomical units, which by the standards of what we were seeing around other sun-like stars was almost modest. Some of the disks imaged around stars similar to our sun extended to 100, 150, even 200 astronomical units. The natural conclusion was that our solar system was unusually compact at its outer edges. Some researchers suggested this might be a side effect of the particular dynamical history our giant planets went through. The upheaval that produced the NICE model's orbital reshuffling had maybe truncated our disk more severely than average. That conclusion is now in serious doubt. When the New Horizons team used the Subaru telescope to push observations of the outer solar system to fainter detection limits and greater distances, they found objects at 70, 80, even close to 90 astronomical units. Not one or two anomalous bodies, but a statistically significant population. A second belt, or at minimum an extended outer edge to the belt we already knew. Researcher Wes Fraser put it plainly. Our system had looked compact, partly because we hadn't been searching carefully enough at the right distances. The signal was there. We had been missing it because the objects are extraordinarily faint at those distances and move with painful slowness across the sky. This changes the picture considerably. A solar system with detectable structure out to 90 astronomical units is no longer an outlier. It is consistent with the extended debris disks we observe around other stars. The apparent anomaly dissolves once you correct for what we were capable of detecting versus what was actually there. And that correction matters, because it means our solar system might be far more typical than the truncated picture implied. The hidden outer reaches were always there. The maps were just wrong. What comes with that realization is something more interesting. If our system has a gap between roughly 55 and 70 astronomical units, an extended population beyond that, and an abrupt inner edge somewhere around 50 astronomical units that we call the Kuiper Cliff, that is a complex, structured architecture. Gaps on both sides of a distant population, multiple belts, an abrupt boundary. These are not random features. In any protoplanetary disk around another star, this kind of structure would immediately prompt a search for the bodies responsible. Astronomers studying those systems don't assume the structures are random. They model the gravitational influence required to produce each feature and work backward toward a predicted planet mass and orbit. It is systematic detective work, done at distances of dozens of light years, using only the shape of a glowing disk as evidence. We are now doing the same thing, but from the inside. And we have far better data than we could ever gather on a disk around a distant star. The individual objects in the Kuiper Belt are measurable. Their orbits are trackable. The clustering patterns that point toward Planet 9 are a level of detail that no external observation of another system could possibly reveal. We are, in effect, reading our own debris disk with a resolution that will never be matched by anything we observe from across the galaxy. The irony is that this comparison cuts both ways. Every time astronomers find a gap in a disk around another star and attribute it to a hidden planet, they are applying reasoning that was partly built on what we understand about the Kuiper Belt. Neptune's resonant sculpting of Kuiper Belt populations, the way large bodies clear their orbital paths over time, the statistical signatures of gravitational shepherding. These ideas were developed here, using our own system as the laboratory, and they have been exported outward to interpret what we see everywhere else. And now the lessons are flowing back in the other direction. The extended populations, the structured gaps, the signatures of dynamical instability from billions of years ago. All of it is reminding us that our system is not a finished, settled thing with a neat outer edge. It is a record of violence and migration and sculpting that is still being read. Every other planetary system with a debris disk is probably telling a similar story. The details differ, the histories differ, but the processes are the same. What we have been learning about the Kuiper Belt is not just a story about our own solar system. It is a key for reading the architecture of every planetary system in the galaxy. 30 years ago, the Kuiper Belt did not exist as a confirmed place. It was a theoretical region, a placeholder on a map, something astronomers believed had to be there but had never actually seen. Today, it is one of the most actively studied frontiers in planetary science, and the closer we look, the stranger it becomes. Think about what has been found in just 3 decades of serious observation. A frozen body 500 kilometers wide, carrying an atmosphere that the models said was physically impossible. Dwarf planets at the edge of the solar system, showing hints of internal heat and possible liquid water beneath their surfaces. Objects sitting at 80 and 90 astronomical units, nearly double the distance where the Kuiper Belt was supposed to end. A gap in the outer solar system between 55 and 70 astronomical units that has the exact shape and character of a cleared orbital path. A clustering pattern in the orbits of distant objects that has resisted explanation for a decade and that points persistently towards something large and unseen. None of this was in the textbooks when David Jewett found 1992 QB1. All of it has been found since. The Kuiper Belt is 4.6 billion years old. It has been sitting at those distances since before the first multicellular life appeared on Earth, since before the continents reached anything close to their current shapes, since before the oceans had the chemistry they have now. It is one of the oldest undisturbed archives in the solar system, and for all but the last 30 of those 4.5 billion years, we had no idea it was there. What we have learned since 1992 is genuinely extraordinary. What we have not yet learned may be more extraordinary still. Here is where things stand. The Vera Rubin Observatory began scientific operations in 2025. Its camera is the largest digital imaging instrument ever built for astronomy. In its first year or two, it is expected to discover roughly 35,000 new Kuiper Belt objects, nearly 10 times the entire currently known population. With that volume of data, the orbital clustering that has anchored the Planet 9 hypothesis either holds up under proper statistical scrutiny or it doesn't. The observational bias argument, which has kept the debate unresolved for nearly a decade, essentially collapses under sample sizes that large. The answer is coming. It may already be sitting in the first Rubin data releases right now, and the answer splits into 2 directions, both of which are almost unsettling in what they would mean. If the clustering is real and a planet is responsible, it is a world somewhere between 5 and 10 times the mass of Earth, orbiting at hundreds of astronomical units on an elongated path so wide that it takes between 10 and 20,000 years to complete a single trip around the Sun. Finding it would be the largest discovery in planetary science since Neptune. Larger, arguably, because Neptune's existence was predicted from a single anomaly in one planet's orbit. Planet 9, if it is there, has been herding objects across the entire outer solar system for billions of years without anyone knowing it. That is not a minor oversight. That is the solar system keeping a secret for the entirety of human history. If the planet is not there, the problem does not go away. It gets stranger. The orbital clustering still needs an explanation. The Kuiper Cliff still has no clean answer. The gap between 55 and 70 astronomical units still looks like the work of something that swept that region clear. If no planet did it, then either the formation history of the outer solar system is more violent and unusual than any current model captures, or the gravitational framework we use to describe motion at those distances is subtly wrong. Modified Newtonian dynamics waiting in the wings as an alternative is not reassuring. It means the problem goes deeper than a missing planet. Both outcomes are real discoveries. Both would reshape what we think we know. The solar system either has a hidden world we have never catalogued, or the physics we use to describe the outer solar system needs revision at some level. There is no version of the answer that is small. Whatever is hiding out there beyond the cliff, beyond the gap, in the cold dark at distances, our maps have always marked as empty. We are closer to finding it than we have ever been, and the answer, when it comes, is not going to be small.